what we're going to have a look at is new stuff tonight, further analysis of real transformers. We're going to look at how this complete model that we developed last week, with all them inductors and different bits and pieces in, for both to model the whole transformer, open and closed circuit, or open, unloaded and loaded version. We're going to be able to simplify that model for both the loaded condition and the unloaded condition, and explain the reasons why. And that's still a valid model. Okay, that second bit on there, determine the model values for a practical transformer. We're going to be doing that next week. So I've juggled things around a little bit, but I couldn't change that slide because that's an image. Okay, so we'll be looking on that next week. So let's have a look at this page here. So there's our full model that we developed last week. Now I'll just go through that. We've got our generator here, and these are the input terminals to the transformer. You can actually put your meter on those two terminals, and that's the only place on that side of the transformer you can. These, remember, are just imaginary components representing losses inside the real transformer. You cannot put your meter there, or anywhere in that internal circuit there. This is a model. These two components represent the offload current that will flow. So even if you've not got anything connected to the secondary, current will flow through the coil that is the primary winding, and that primary winding will have inductance to represent the magnetizing current of that coil, and resistance to represent the power loss, mainly in heat, heating up of the core and the cables and everything. These two components represent, well, essentially the on-load losses. This one represents the heating in the core, in the winding of the coil, the resistance of the coil. And this one represents the flux that is not linked between the two coils, so leakage flux on the primary side. And then on the opposite side, on the secondary side, when it's open circuit, no current flows in the secondary, so we've not got anything equivalent to these two, but we've got an equivalent to those two that represent the resistance and the leakage flux in the secondary side. Again, these two terminals here are the only places on that side of the transformer that you can actually put your meter and take measurements. Okay, so that's the complete transformer model that we could then add a load to and use some transfer and impedances method of calculation to actually do analysis on that circuit if we had some values. So that's the full transformer model from last week. Okay, that circuit has far more detail than is really needed to solve most practical problems. It's possible to simplify that model by considering its action, one, when it's off load, and two, when it's at full load. Okay, and I'm going to explain why that is now. So we've developed a full model, and now we're going to look at how it can be simplified. So the facts are, if there's no load, there's no current flowing in this secondary side here, 0 amps. So because T1 is ideal, then I1 going into the transformer, just this circuit, part of the circuit here, must also be 0. Yep. So the only current flowing is the current that flows in there and goes down through those two components. Yep. This means that the components R2 and X2 have no effect and can be ignored. So we can forget those two. They don't do anything. The impedance of R1 and X1 so small under this quite low current off-load condition compared to the value of these two components. So the value of these two is very small compared to the value of those two, and therefore under open circuit conditions their effect is negligible and we can ignore them. Don't forget about those two. Therefore, to analyse what this circuit will do under no load conditions, we can revise that circuit to simply the two components representing the magnetising current and the heat in the coil that we looked at in the first place. Okay? And really, the reason you want to analyse that circuit is because one way of finding out on a real transformer what these component values are to do what's called open and closed circuit test, which is what we're going to be looking at next week. And by doing open closed circuit test, you can find out what the values of those two components are and the total value of these components as well. We'll come on to that in a minute. And we're going to do that hopefully on that transformer on the rig there and prove that all these calculations actually work for a real transformer. And I think that's quite important to do that, otherwise it's just kind of a maths exercise rather than actually seeing that this model is realistic and it does work. Yep. So we get a revised model if we want to analyse this transformer in its open circuit condition. We could ignore the leakage flux. It's negligible compared to the effect of the two parallel components, RC and XM. Okay? Everyone happy with that? So that's on. Now, if we want to consider the real transformer on full load. On full load, the primary current, IP, this current here, at full load, is at least 20 times, on a practical transformer, at least 20 times larger than this small current that flows in here. So that the current that's magnetising the core, the losses for the open circuit condition, are now negligible compared to the current that's flowing when the transformer's on full load. Okay, so what that means is on full load we can effectively ignore those two and have so little effect in the total result that we can forget about them. Okay? This means that we can revise the equivalent circuit for the real transformer at full load to be that circuit without those two components. And again, we could analyse that circuit, and we have done some circuits similar to that last week. Okay? So, and it's actually suitable for this transformer model to be used on a transformer that's only loaded at 10% of its full load, and that's still valid to make that simplification. There's a significant difference between that current and that one up there. Okay? Then what you can do, having done that, we can then go through our process of transferring these two components to the other side of the ideal transformer in the middle. Yeah. So when we know we would do that, because that's the only real way we can analyse what's going on with those two components, and we end up with that circuit. So we simplify the circuit by bringing R2 across, we multiply by A squared, bringing X2 across by multiplying by A squared, A being the transformer ratio, N1 over N2, and we multiply the load impedance by A squared as well, and we multiply secondary voltage by A. Yeah. Everybody happy with that? Okay. So we've got an even simpler model now by using transferring impedances. And then we can go one step further than that even. The primary and reflected secondary impedances can then, if need be, combine together. So what we can do now is take those two and combine them with them two. We effectively R1 plus A squared R2 and X1 plus A squared X2. Add the real and imaginary components together into one impedance. And the reason we can usually do that is because we ain't really interested in what the volt drops across each of those individual resistor and inductive components are. We're interested in the total effect of them added together. Yeah. So we make that into one R, one X component with one current flowing through it by adding the two together. So that's the resistance and reactance as below only need to be separated if you're interested in their individual values. If you're not, then they can be left together. Okay? Anybody totally confused by that? And we'll use that circuit to analyse what our closed circuit conditions are for the transformer and get some values. Okay? So, having done that, let's have a look at an example analysis for each of those conditions. First of all, we got a circuit of a transformer where we're in open circuit condition. Okay, so we can do the first simplification on here, which is, what can we ignore here? That's offload, yeah? Yeah, we can certainly ignore them, because if nothing's connected this side, there's no current, so they're not going to do anything. Yeah. And these two, because their values are small compared to these two, we can ignore them as well. Yeah. So effectively, you've got the circuit that's on the next page. I've drawn for you. That one there. I made it a bit small up here. So I've taken out the two series components on both sides of the transformer, and now we can do the open circuit analysis of that transformer on that. And the question says, A, find the open circuit primary current. A, find IO. How are we going to do that? Might help if we went and put the values we've been given on the circuit. So primary voltage 11 kV, This is 400 volts. RC 27.5 K and XM 16.5 K. This is a big transformer. Yeah, so we can find I/O. No, if you use that, you're going to find the loaded current. Yeah? There you got total impedance. Yeah? Okay. So how do I do that then? I knew I had a version with the answers on somewhere. How are they connected? In parallel. So ZT parallel. You can do the 1/. There's only two, so what's the quickest way? Product over sum. Yeah? Do RC XM over RC plus XM. Yeah? We got 27,500 ohms multiplied by 16,500. What do I need to add to that for the inductor? Angle. The inductor is, you got it right first time, 50-50 chance. Like that three-phase motor, is it going to go anti-clockwise or clockwise? 50-50 chance. What's the easiest and quickest way to express that bottom line straight off the bat? Yeah, that's plus 0J. And the other part, the X part, is 0 plus, so simply like that. Okay. How are we going to finish off that? What's your favoured way to finish off that complex arithmetic, bearing in mind we've got a numerator that's polar and a denominator that's rectangular? Convert the bottom one. Yeah. So what we could probably do is multiply out the top one straight off and convert the bottom one and then do the division. Which one? That's 90, yeah. Gemma, sorry.
What is one polar, one rectangular?
That's just only in the, that's the easiest way to write them, Richard. Because the top lines come out of multiplication, yeah, and the bottom lines, there's a division in there. There's, with multiplication you'd prefer polar, yeah. With division you prefer polar, but here we got an addition that we can get from rectangular, yeah. So what we're going to do is multiply out the top line, and convert the bottom line so we can then do the division. Alright? So we're going to multiply out the top first and then divide. I'll let you finish that off and give me the results. So we got for R2 dash then. 3 ohms. And X2 dash 15 ohms. What about ZL dash? We're going to have to do that times a complex number, aren't we? 2 plus 1.5. Okay. Got to do that times that separately from that times that. Just like any. Sorry? 1513 will do then. No, you've got to do that times that and multiply by J. So you've got to do 1.5 times. This is like, if we write that as a complex number, that's 27.5 squared plus 0J. And then when we multiply the two together, don't we? But we can ignore that fact, just multiply everything outside the brackets by what's inside the brackets. So we do 1.5 times 27.5 squared. One, 1, 3, 4. J. And that's ohms. Okay. Let's just convert it to polar as well. So that's rectangular form. Polar, we might want it in polar form later. So we might as well do it now. One 1891 ohms, angle 37 degrees. Yep. So we may well need to use that in either or sometimes even both of those forms. So that's handy just to do it there, keep them both in the same place. Yep. And that's Z1 dash is equal to that. Right? Okay. So what we've got now is, oh, I've gone back that bloody thing again. No, that's for analysis. We've transferred secondary components here over to the primary side and got rid of our ideal transformer. So the first actual part of the question said find the primary current. So find I1. So how can we do that? Yeah, ZT. All right. We've got values for R1, 2.7 ohms. We've got value for X1, 13.7 ohms. Well, what we've got, how can I write that in rectangle? We've got this in rectangular form if we want it. Can we write these two in rectangular form easily? What would that one be? This one. The R1 and X1. How could I express that in rectangular form? 2.2 plus 13.1J. So this is equal to R1 plus X1J, that is 2.2 plus 13.1J plus R2 dash plus X2 dash J, that's 3 plus, is that 15? 15J plus ZL dash, which is 1513 1134J. And now doing it that way make them easier to add up, because you add up that column and that column separately. Yeah? By no means fully loaded. All right, what do we get? Yeah, so let's say 1519, shall we? Argument. Plus 1162J ohms. Yep. So we'll just summarize that there. ZT is equal to, in rectangular form, 1519 plus 1162J. Polar form, we'll do the conversion now because we might want it in that form. (1913) then plus 37.4 angle 37.4. degrees. And that's ohms, and that's ohms. Okay. Now can we calculate IP? How do we do that? Yeah, we'll go with EP, same thing but different, over ZT, 11,000, angle nothing, over 1913, angle 37.4 equals 5.75 amps, angle 37.4. Civil says, yeah, that's good, because it's inductive, and we got a negative angle. Yep, lagging, current's lagging. Okay. So we now found the primary current flowing under this load. Now we know that full load, design full load current's 20 amps. So this thing is only 25% loaded. Still significantly more than that small 0.8 of an amp flowing off load. So it's still negligible in terms of that. All right. The next thing is to find the voltage at the secondary terminals, ES. So we want to find the voltage across here, that voltage, but what it is actually on the secondary. We know this, that's ES dash. We can find that now. E2 dash, secondary voltage transferred to the primary side. And we know that E2 dash is equal to I times E2. So if we can find that, we can use that formula to transfer it back to the primary side and find out what it really is. Yeah? So how can we find E2 now? B. We just said we'll first find E2 dash. E2 dash is equal to formula to find that now. Sorry, ZT dash times IP. Yep. It's not ZT dash. Got that wrong. You led me up the garden path. Z1 dash, ZL dash, sorry. This impedance here, yeah, just the impedance of the load transferred to the primary side. So you want this 189, who is it? Angle 37 degrees. Check it on here. Z1 dash 1891 angle 37 degrees. In actual fact, if you carried all your rounding through, if you've done all these calculations exactly, those angles should cancel out. Should be no phase voltage, primary and secondary, in phase with each other. That's just that as rounding errors in those two angles there. I mean, they don't. Yeah, so they actually, in reality, they would cancel out if you carried all your calculations through. So we can essentially assume they do cancel out. Do you see what I mean or not? Yeah. So what do we get when we multiply 1891 by 5.75? 10,867 volts, angle 0 degrees. Actually, that's what I got on my piece of paper, to be honest. 5.75. Okay, well, yeah. We're probably including too many significant figures here anyway, really, but let's go. We'll go with what we got on the board there now. Don't, you know, our number here and there ain't going to make that much difference to us. All right. So that is E2 dash. E2 dash is equal to A times E2. Therefore, E2 is equal to E2 dash over A. So we're now transferring that voltage back to its rightful place on the secondary side. E2 is equal to 10867 divided by 27.5. $395 volts, angle 0 degrees. Right, yeah. Now, I'll just give me 1 minute, Richard. Okay. So what we've done now is we've calculated that voltage there, 395 volts. So you can see now what's lost across this pair of components and that pair of components, which are the linkage losses between the two terms of the transformer. The next part of the question says, right, determine the current flowing in the load. Okay, now we know that I1 or I2, we could say I2 dash is equal to I1 and then transfer it back over, or we could use that voltage with the load to find the secondary current. It wouldn't matter, we should get the same answer both ways. So in an exam question now, if you took this current flow in here that we calculated earlier, I1, and said that's also equal to the current I2 dash, and I2 dash is equal to I2 divided by A, and change that formula round and get the answer. Or you could use this voltage we just calculated, 395 volts, with the original the original 2 plus 1.5J load, find the current flowing in the secondary. So you could do that either way. Right? See that, Richard? And I just want to get that across, that there's two ways to do that before you went. Right? This stuff will be put up here, and I'll also do a video if I go through any of the tutorial questions. I'll just give you them as well, Richard. Hang on.